Hey everyone, welcome back to Control System Lectures. We had started our discussion on feedback linearization from the last video, and we studied that it is possible in two forms. Firstly, input state linearization and then input output linearization. Of this, we have studied about input state linearization and also saw a solved example on the same. In this lecture, we will start discussing about input output linearization. Firstly, I will introduce you to some terms which you should become familiar with, and then we will proceed to our topic of interest. So, let's start our lecture. Suppose we have a class of single input, single output system of the form x dot equal to f of x plus g of x into u and y equal to h of x, where f of x, g of x, and h of x are nonlinear functions and x belongs to Rn. Also, f, g, and h are sufficiently smooth in a domain D subset of Rn, and the mappings f from D to Rn and g from D to Rn are vector fields on D. So, we have a space Rn in which we have our domain of interest D. In case you are unfamiliar with vector fields, it is basically an assignment of a vector to each point in a subset of space. For instance, a vector field in a plane R square can be visualized as a collection of arrows with a given magnitude and direction, each attached to a point in the space. As students of engineering, you might have already encountered vector fields from the first year onwards, right? So I'm not discussing about it further. Now another term I would like to introduce is Lie derivative. Suppose I am taking the time derivative of the output y equal to h of x. So time derivative will be y dot equal to d by dt of h of x, which will be dou by dou x of h of x into dx by dt, right? And this will be dou h of x by dou x into x dot. And we know that x dot equal to f of x plus g of x into u. For the time being, I am assuming that u is absent, so the term g of x into u will be 0. Therefore, x dot will be simply equal to f of x. So, this will be dou h of x by dou x into f of x. And this can be written as Lie derivative of h of x with respect to f. This is just a handy notation, that's all. Okay. Now, the next term we need to learn is relative degree of output. Relative degree of output is basically the number of times you have to differentiate the output before the input explicitly appears in your output equation. Let's take an example to understand this better. Consider the system x1 dot equal to x2 and x2 dot equal to minus x1 plus epsilon into 1 minus x1 square into x2 plus u, and the output is y equal to x1. Calculating the derivative of the output, y dot equal to x1 dot, and this is equal to x2, therefore x2, and you can see that the input is not explicitly appearing in this equation. Therefore, we will take the second derivative, y double dot equal to x2 dot, and this will be minus x1 plus epsilon into 1 minus x1 square into x2 plus u. Therefore, minus x1 plus epsilon into 1 minus x1 square into x2 plus u. So you can see that after the second differentiation, the input u is explicitly appearing in the output equation. So the relative degree of system in this case is 2. Relative degree is equal to 2. On the other hand, if the system output was y equal to x2, differentiating is as y dot equal to x2 dot, which is equal to minus x1 plus epsilon into 1 minus x1 square into x2 plus u. You can see that After a single differentiation, the input u is explicitly appearing in the output equation. So the relative degree of output y in this case is 1. Relative degree is equal to 1. So you got an idea about relative degree, right? However, relative degree may not always be well defined. For instance, consider the system x1 dot equal to x1 and x2 dot equal to x2 plus u and output y equal to x1. Calculating the derivative of y dot equal to x1 dot and x1 dot equal to x1, therefore x1, which is again equal to y only, right? Let's differentiate again. So y double dot equal to y dot, which will be equal to x1 dot and x1 dot equal to x1, and this will be equal to y. So we can see that the nth derivative of y will be equal to y, which will be equal to x1 for all n greater than or equal to 1. No matter how many times you differentiate the output equation, the input u won't explicitly appear. So in this case, the system doesn't have a well-defined relative degree. That is, doesn't have a well-defined relative degree. We can also prove this analytically. We know that the output equation is y equal to x1. And from this equation, we can see that x1 is equal to y dot. Therefore, this can be equated as y dot. Writing this again, y dot equal to y, which implies dy by dt is equal to y. This on rearranging gives us dy by y is equal to dt. Integrating on both sides gives us ln y plus c equal to t, where c is the constant of integration. Now at t equal to 0, we have y equal to y naught, which will be x1 of 0. Plugging this into this equation gives us ln of y naught, which will be ln of x1 of 0 plus c equal to 0. This gives us c equal to minus ln x1 0. Putting this back into the original equation gives us ln y minus ln x1 of 0 is equal to t, which is ln y by x1 of 0 equal to t, which will be y equal to x1 of 0 into e raised to t. From this we can see that the input u does not appear explicitly in the output equation. This is the reason why we did not obtain a well-defined relative degree for the system. Okay, now that you have an idea about Lie derivative and relative degree, let us bring back our focus to the topic of interest, that is input-output linearization. Our system model was x dot equal to f of x plus g of x into u and y equal to h of x, where f maps from D to Rn and g maps from D to Rn and D is a subset of Rn. Our system is nth order and let k be the relative degree of the system. That is, k be the relative degree of system. Now this k has to be either less than or equal to n. If k is equal to n, then it means that the system is fully feedback linearizable. And if k is less than n, it means that the system is only partially feedback linearizable. Let us now take the first case, k is equal to n, that is, when the relative degree of system is exactly equal to the dimension of state space at some point x equal to x naught. Let us differentiate the output y equal to h of x, which gives us y dot equal to dh of x by dt, which will be dou h of x by dou x into x dot, and we know that x dot is equal to f of x plus g of x into u. Therefore, dou h by dou x into f of x plus g of x into u. This gives us Lie derivative of h of x with respect to f plus Lie derivative of h of x with respect to g into u. Now listen carefully. We have assumed that the relative degree of system is k. This means that the output should appear explicitly only on the equation corresponding to the kth derivative. Therefore, this term has to be 0 so that y dot is independent of u. If we continue to calculate the second derivative, y double dot, also I'm changing the notation, okay, is equal to d by dt of Lie derivative of h of x with respect to f, which is dou by dou x of Lie derivative of h of x with respect to f into x dot, which will give us dou by dou x of Lie derivative of h of x with respect to f into f of x plus g of x into u, which is equal to LF square into h of x plus Lg into LF h of x into u. Again, by the previous logic, this term has to be 0. Similarly, if we go on, at the kth derivative we have LF k into h of x plus Lg into LF k minus 1 into h of x into u. Here this term has to be non-zero, as we had assumed that the relative degree of system is k, and therefore the input u has to be present in the equation. Okay. Now that we have input u present in the output equation, we will choose u such that it cancels out the non-linearities present. So if we choose u such that u is equal to 1 by Lg Lf k minus 1 into h of x into b minus Lf k into h of x, and plug this u into this equation, the input output map reduces to kth derivative of y is equal to v. Therefore, now we can obtain y by integrating v k times. This k times v. That is, provide a chain of integrators before y. Now, if I write this as phi 1 of x, this is phi 2 of x, this is phi 3 of x, and similarly if I write everything down, we get phi of x is equal to phi 1 of x, phi 2 of x, etc. to phi k of x is equal to h of x, Lf into h of x, etc. to Lf k minus 1 into h of x. Let us do a change of coordinates now. Therefore, defining zi is equal to phi I of x is equal to Lf I minus 1 into h of x, where I lies in the range 1 less than or is equal to I less than or equal to k. Also in this case we have assumed k is equal to n. Therefore 1 less than or is equal to I less than or equal to n is also true. And using this definition we can write phi of x is equal to z1, z2, etc. to zn. We can see that Lf h of x is the time derivative of h of x. Therefore, z2 will be the time derivative of z1. And similarly, z3 will be the time derivative of z2. Therefore, in the new coordinates, the system will appear as described by the equations of the form z1 dot is equal to z2, z2 dot is equal to z3, etc. to Zn minus 1 dot is equal to Zn, and Zn dot is equal to V, where V is equal to LF n h of x plus LG LF n minus 1 h of x into u, where x is equal to phi inverse of z, and z is equal to z1, z2, etc. to zn. Now I hope that everyone understood how we obtain these equations. And in case you have doubt about the last equation, by our definition we have Zn is equal to phi n of x, and since k is equal to n, we can write this as phi k of x. And what was phi k of x? Is equal to Lf k minus 1 into h of x. Therefore, is equal to Lf k minus 1 into h of x. Now if we take the derivative of Zn, Zn dot is equal to d by dt of Lf k minus 1 into h of x, and this is dou by dou x of Lf k minus 1 into h of x into x dot, and we know that x dot is equal to f of x plus g of x into u. Therefore, Zn dot is equal to Lf k h of x plus Lg Lf k minus 1 into h of x into u, and we have defined u as 1 by Lg Lf k minus 1 into h of x into v minus Lf h of x. Let me copy paste that. So this was u, and substituting this u over here gives us Zn dot is equal to v, and that is how this equation came into picture. Also recall that Z0 is equal to phi of x0, and thus at all z in the neighborhood of Z0, the function Lg Lf k minus 1 into h of x will be non-zero. And why is this important? Because this expression lies in the denominator and therefore has to be non-zero. Okay, so here is our resulting closed loop system, which is linear and controllable. So the linear state model is Z dot is equal to AZ plus BV and Y is equal to CZ, where A is equal to, we know that Z1 dot is equal to Z2, therefore 0, 1, 0, etc. to 0, and we know that Z2 dot is equal to Z3, therefore 0, 0, 1, etc. to 0, and going down similarly 0, 0, 0, etc. to 1, and we know that Zn dot is equal to v, therefore no z terms are present, so all the terms are 0 in the final row. Note that this is an n into n matrix, and we have b is equal to, only the last term Zn dot have v, therefore 0, 0, 0, etc. to 0, 1, and this is an n into 1 matrix, and finally we have c is equal to, we know that y is equal to h of x, which is equal to z1, therefore the first term is 1 and all other terms are 0, etc. to 0, and this is a 1 is to n matrix. Also keep in mind that z is equal to phi of x, where phi of x is this one. Let me copy this and paste it here so that the picture is complete. Look at that now, it's looking beautiful, right? Thus we conclude that any nonlinear system with relative degree n at some point x0 can be transformed to a system which in the neighborhood of the point z0 equal to phi of x0 is linear and controllable. Also, it is important to stress that the transformation in question has two basic ingredients: a change of coordinates defined locally around the point x0 and a state feedback also defined locally around the point x0. But this only covers a particular case of the input-output linearization, that is, when the relative degree is equal to the order of the system. We have another case left the case where k is less than n. But I feel like discussing that also in this lecture will be an overkill. So I will talk about that in the next video. Now before ending the lecture, let us take a small example so that the concept becomes clear. We have the system x1 dot is equal to x2, x2 dot is equal to minus x1 plus epsilon into 1 minus x1 square into x2 plus u, and output is y is equal to x1. Differentiating the output, y dot is equal to x1 dot and y double dot is equal to x2 dot, which is minus x1 plus epsilon into 1 minus x1 square into x2 plus u. You can see that in the second differential, the input u is explicitly appearing, so that the relative degree k of the system is 2, and this is equal to the order of the system, as you can see from the question. So as you learned, this system is fully feedback linearizable. Now we choose the input u such that y double dot is equal to v. Therefore, u is equal to v plus x1 minus epsilon into 1 minus x1 square into x2. Also proceeding as we studied, let y is equal to phi1 of x and y dot equal to x1 dot is equal to phi2 of x. And we set zi is equal to phi I of x, where 1 less than or equal to I less than or equal to 2. Therefore, z1 is equal to phi1 of x, which is x1, and z2 is equal to phi2 of x, which is equal to x1 dot, and we know that x1 dot is equal to x2, therefore is equal to x2. In the new coordinate, the system appears as z1 dot is equal to z2 and z2 dot is equal to x2 dot, which is b, and y is equal to phi1 of x, which is z1, therefore z1. So in the state space model, we can write z dot is equal to 0, 1, 0, 0 into z plus 0, 1 into b, and y is equal to 1, 0 into z. So you can see that we made the nonlinear system into a linear controllable system. Note that the basic feature of the system that made it possible to change it into a linear and controllable one was the existence of an output function h of x, for which the system had a relative degree equal to n at x0. The existence of such a function is not only sufficient but a necessary condition for the existence of a state feedback and a change of coordinates, transforming the given system into a linear and controllable one. That's all for this lecture. I know this concept is difficult to grasp at the first go, and it may require you to view it multiple times to understand the concept properly. If you have any doubts, you are always welcome to drop them in the comment sections below. In the next video, we will continue our discussion on feedback linearization and hopefully conclude this topic. Thanks for watching and have a nice day.